Hi everyone, we are Bidyut, Disha, and Jaspreet, and our project looks at sleep health and lifestyle. The question that pulled us in is one most of us have wondered personally. What actually shapes how well we sleep? Is it how much we move, how stressed we are, our weight, or our job? We took a data driven approach to find out, and we will walk you through what we asked and what we found. Next. Our core research question was which lifestyle factors are the strongest predictors of sleep quality, and can we use those factors to classify someone as having good or poor sleep health? To get at that, we focused on sleep duration, stress level, physical activity, occupation, and BMI, and tested whether they explain how well we sleep. But we didn't want to stop at single factors. We also asked how these variables interact with each other and whether certain groups, say by occupation, age, or BMI category, are more vulnerable to poor sleep than others. So the goal was both prediction and understanding who's at risk. Next. For data, we use the sleep health and lifestyle dataset from Kaggle. It gives us 400 individual records, each with 12 lifestyle and health variables. The age range is broad, 18 to 90, so it's not just one demographic. A couple of numbers worth anchoring on. Average sleep duration sits in 7 to 9 hour range, and the average sleep quality score is about 6.1 out of 10. And importantly, after cleaning, we had zero missing values, which meant we could move into analysis without making any heavy assumptions. Next, please. Getting there took four cleaning steps. First, we handled missing data. About 290 rows had a blank in the sleep disorder column, and rather than treating those as errors, we recognized a blank meant no disorder, so we filled them with none. Second, we standardized the structure, trimmed, and renamed columns for consistency. Third, blood pressure came as a single combined field, so we split into separate systolic and diastolic columns to give us a real numeric features. And fourth, we encoded all the categorical variables using both label and one-hot encoding, so the data was fully numeric for modeling. The end result, a clean, complete, and numeric data set ready to analyze. Now, Jaspreet will take us into what the data actually looked.
Thank you, Disha. When looking at the distribution of sleep quality scores, we see a roughly bell-shaped curve that leans a little to the right and is centered around a moderate score of 6 out of 10. The most common scores are 5, 6, and 7. Very low scores are 1 or 2, and very high scores are 9 or 10, making both high and low scores rare. This tells us the population isn't polarized into clear good sleepers and bad sleepers. Most people are somewhere in the middle, which actually suggests more room for improvement. We then looked at each major predictor individually. For stress level, the median sleep quality stays flat across all stress groups, which was a surprising find. The median stayed usually around 6, and the correlation was basically 0. For physical activity, the regression line is almost flat, and the people with both low and high activity levels had sleep scores spread across the full range. BMI categories show heavy overlap with identical medians around 6, showing BMI by itself doesn't predict sleep quality. And people with different sleep disorders like insomnia, sleep apnea, or none all seem to cluster around the same center near 6. The takeaway from the exploratory data analysis is consistent. No single variable has a strong, clear relationship with sleep quality on its own. The correlation heat map confirms what the plot suggested. Every variable's correlation with sleep quality sits near 0, under 0.08. Heart rate is the highest at just 0.07, while sleep duration is essentially 0, at negative 0.002. Stress level at negative 0.15, physical activity at negative 0.03, and daily steps at negative 0.04. None of these reach even a weak linear relationship threshold. This guided our modeling decision. Since the signal isn't clear, we turned to a tree-based approach. We trained a random forest regressor on all 12 features using an 80-20 trace train test split with a random state of 42. We tested both label encoded and one hot encoded versions of the data, and both produced nearly identical results. The model achieved a mean absolute error of 1.68, which signifies predictions were off by about 1.7 points on a 10-point scale on average. And the R squared score was negative 0.19, which means the model actually performs worse than just predicting the mean sleep quality for everyone. The features in this dataset simply don't contain enough signal to predict sleep quality reliably. Now I will pass it on to Bidyut.
Thank you, Jaspreet. So next step, we did feature importance analysis to identify which variables they have the greatest influence on the model's predictions of sleep quality. So it showed physical activity was the strongest predictor of sleep quality, followed by daily steps and age. Sleep duration, heart rate, and blood pressure, both systolic and diastolic, also contribute meaningfully to model predictions. In contrast, variables such as gender, occupation, BMI category, and sleep disorder status, they have relatively low importance. However, despite the identified key predictors, the model's low overall explanatory power suggests that additional factors influencing sleep quality were not captured in this dataset. Next, please. This slide summarizes the three major findings from the project. First, there was no dominant predictor of sleep quality. Through EDA analysis, correlation analysis, and feature importance evaluation, no single lifestyle or health factor consistently showed a strong relationship with sleep quality. Even variables which are commonly associated with sleep, such as sleep duration, stress level, they showed weak relationships in the dataset. Second, the machine learning model was unable to accurately predict sleep quality. The random forest model produced a negative R score, indicating the available features did not contain a strong predictive signal. This suggests the sleep quality is difficult to estimate using these variables alone. Finally, the results indicate the sleep quality is likely a multifactorial outcome. It is probably influenced by a combination of complex and unmeasured factors which are not captured in this data set. Those factors likely are mental health, sleep environment, genetics, diet, caffeine intake, and other behavioral factors. Overall, this project shows that sleep quality cannot be explained fully by the basic lifestyle and physiological measures alone. Next, please. Like any other data science project, this study has also some limitations. First, the dataset contains a relatively limited set of features. Important factors that can influence sleep quality, like mental health, caffeine intake, screen time, sleep environment, they are not included in the data. Second, sleep quality was measured using a self-reported scale of 1 to 10. Because this measure is subjective, different individuals may interpret it different ways and they can rate sleep quality differently, which can introduce noise into the dataset. Third, the dataset contains only 400 observations. While it is sufficient for EDA analysis, but a larger sample would improve the reliability and generalizability of the findings. Looking ahead, future research could incorporate richer behavioral and health-related variables and explore larger longitudinal data sets and validate results of using objective sleep measurements collected through wearable devices or clinical studies. These improvements may help uncover patterns that are not detected in this current dataset. Now, although this model didn't accurately predict sleep quality, the project provided valuable insight by showing that sleep health is a complex multifactorial phenomenon that cannot be explained by simple lifestyle measures alone. Thank you for listening to us.